Okay. In order to talk about the fundamental theorem of algebra, which states that every polynomial has a complex root somewhere, and then we can iterate to factor things over the complexes, we need to talk about complex numbers a little bit. So let's get started. So we're going to take R, and it would be nice to have a negative square root. So what we do is to R we attach a square root of -1. And how do I mean we attach it? Well, I want this to be a field still. So we have multiplication, we have addition, we have subtraction, we have division, as long as you're not dividing by 0. And it turns out that if we attach it in the way that A plus BI is an element of the complex field, so we're going to take the set of all of these things such that A and B are real, and we'll call that the complex field. And this turns out to, well, I is the square root of -1, i.e. I squared equals -1. It turns out that this is a field. We can still perform multiplication, and how we do that is we FOIL things. So A plus BI times C plus DI, you get AC plus ADI plus BCI plus BDI squared, which is AC minus BD, because I squared is -1, that negative sign goes there, plus AD plus BCI. Okay. And these things are again real numbers, and these are again real numbers, so multiplication is closed, and we can show all of our field axioms for this set. Okay, so this is a nice algebraic way to define the complex numbers. We want a little bit more of an analytic way to define the complex numbers. And so what we're going to do is we're going to define them slightly differently. And let me draw a picture for this. So here's the real axis, and here's the imaginary axis. So this is the complex plane. And we can put A plus BI, say 1 plus 2i, in here by going 1 in the real direction and 2 in the imaginary direction. So this is this point right here would be 1 plus 2i. Maybe this guy down here would be, oops, say this is -3 minus 2i, and so on. We can plot points in the complex plane this way. But it turns out that polar coordinates, in some sense, are the better way to think about complex values. And let's see how that works. Well, polar here is, here's the angle theta, and here's the radius, how far it is from the origin. So 1 plus 2i. So it's going to have r is equal to the magnitude of 1 plus 2i, which is equal to 1 plus 2i times 1 minus 2i. So multiply by the conjugate, and then I have to take the square root. That's going to be the square root of 1 plus 4 is the square root of 5. And then the angle is the arc arctangent of the opposite over the adjacent, because the tangent's opposite over adjacent, so that's going to be 2 over 1, so this is the arctangent of 2. So we could also write 1 plus 2i as we could write it as kind of the polar point, the square root of 5 at an angle of arctangent of 2. Okay, but that's not maybe the best way to do this. It turns out, and the book presents this in the earlier chapters, that I can rewrite this as the square root of 5 times e to the I theta, where this is theta. And why that works is Euler's formula. If you kind of recall Euler's formula, which says e to the I theta is equal to the cosine of theta plus I times the sine of theta. Okay, so if I do that with a point like this, I can multiply 5 times, or the square root of 5 times the cosine of theta plus I times the sine of theta, and end up back where we need to. Let's see this. So if I have that the tangent is 2, then my triangle theta is 2 over 1. This would be the square root of 5. So that the cosine of theta would be the adjacent over the hypotenuse, which would be 1 over the square root of 5. The sine of theta would be 2 over the square root of 5. So the square root of 5 times e to the I theta in this specific theta case is equal to the square root of 5 times 1 over the square root of 5 plus I times 2 over the square root of 5, which is 1 plus 2i, as we wanted. Okay. So Euler's formula allows us to rewrite any complex number as an r and a theta. And so a plus bi and r e to the I theta, where r is how far from 0. This is the modulus of the complex number, and this theta is called the argument of the complex number. Okay. So z being a complex number, we can write as the modulus of z times e to the I argument of z. And that argument of z is sort of the arctangent of the complex part divided by the real part. But this argument of z thing, this e to the I theta thing, is really nice. So let's look at this. For any theta, e to the I theta in magnitude is equal to 1. Okay. Why is that? Well, let's look at Euler's formula again. So this is sort of a little proposition. So e to the I theta in magnitude is the magnitude of cosine of theta plus I sine theta, which is equal to cosine squared theta plus sine squared theta, which is equal to 1. If you multiply by the conjugate, you get the difference of squares, but you have a difference with an I squared in the back term, so that difference turns into a sum, giving you a cosine squared plus sine squared. Okay. Now, how does multiplication by complex numbers work? So multiplication then it's sort of a very geometric process. Okay, so let's look at this. Let's look at, say, z equals r e to the I theta, and let's say y is equal to s e to the I psi. Then z times y is equal to r e to the I theta times s e to the I psi, which is equal to rs. So I just multiply their lengths, their magnitudes, and e to the I theta plus psi is how that exponential operation works, right? If you multiply two things with the same base, you add their exponents. So what happens is the lengths multiply and the angles add. Okay, so if we are multiplying by a value on the unit circle, say z equal to 1, then the multiplication is purely a rotation. Okay, so for example, here's I, and if I multiply by I again, the angle is 90 degrees, right? Or pi over 2 radians. So if I multiply, here's I, if I multiply by I times I should start at I and rotate, start and then rotate 90 degrees counterclockwise. I should end up down here, and this point is at -1. If I multiply by I again, I should rotate another 90 degrees, and I'll end up at -I. If I multiply by I again, I end up here. And so I get this sort of rotation where this is I squared, this is I cubed is -I to the 4th is 1, and then we rotate again, I to the 5th, I to the 6th, and so on. So each multiplication is a rotation by 90 degrees. This also lets us look at other roots of unity. So suppose we wanted to solve I cubed equals, sorry, not I cubed. Say I wanted to solve x cubed is equal to 1. Well, this has a real root for sure. I can plug 1 in there and get back to 1, but it also has two complex roots. It's a degree 3 polynomial, so it should have 3 roots. How do you find them? Well, I want some value where if I rotate through that angle 3 times, I get to 1. So let's look at the circle. I want to find numbers so that when I rotate through 3 times, I get to 1. Well, if I rotate through an angle of 0 3 times, I've only gone through an angle of 0, so I stay at 1. If I rotate through an angle of 2 pi over 3, then I'll get to 4 pi over 3, and then 6 pi over 3, which is back to my 0, my angle at the origin. And so my angles should be 0, 2 pi over 3, and 4 pi over 3. So this leads to e to the I times 2 pi over 3, and e to the I times that as my 3 roots of unity for the cubic. And so we can calculate these. E to the I times 2 pi over 3 is equal to the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3, and that would be That's a 60-degree angle, so this is going to be the cosine. That's going to be 1/2 plus the square root of 3 over 2i. And this one, it'll be similar. E to the I times 4 pi over 3 is 1/2. Well, it's the conjugate of the first root is e to 1/2 minus square root of 3 over 2i. And we can do that with degree x to the 5th or x to the 7th or x to the 6th. I can just split that circle up into 6 equal angles or n equal angles and get the n roots of unity. Okay. So this idea of angle rotation is pretty powerful. So let's see how this works. Get an application for it that we'll use tomorrow. So for any z in the complex plane, there is a e to the I theta, also in z, or in c. So this is a unit magnitude, unit modulus complex number, such that e to the I theta times z is real. Okay, well, this is just sort of an easy proposition. We write z equal to its magnitude times e to the I times the argument of z. Then we take theta equal to the negative argument. So e to the I negative argument of z times the magnitude of z times e to the I argument of z is equal to the magnitude of z times e to the I times 0, which is just the magnitude of z, which is real. It's actually real and positive. I could get a real and negative from doing the same sort of idea. Instead of solving that I want theta plus the argument to be 0, I want theta plus the argument to be pi. So these processes of this rotation, it's a handy thing to have when we're talking about analysis, and we'll see how that plays together with some limits and some measuring bounds on things and maximizing and minimizing things to give us the fundamental theorem of algebra in the next video.